Good morning, everyone. Today's webinar will be recorded. We'll be going over questions at the end, so please add your questions throughout our presentation today in the Q&A. I'm Craig Seppel, Regional Manager with Excell Battery here in Western Canada. I'm joined today by my counterpart, Bob Fay, Regional Manager with our Houston facility. I want to thank you all for inviting us into your offices at homes. Some of you are dialing in from across the globe today, and we do thank you for staying up to join us. It's really appreciated. One of the things we most enjoy here at Excell is to connect with all of you and participate in the exciting collaborations with the fine folks that put our products to purpose. So before we get started, I just want to affirm to you that we here at Excell are always enthused to hear from you and do so enjoy taking on the most challenging applications that you bring to us. You're all doing that great work of creating the activity and the energy and the vigor of the industries that make our world go round. Excell Battery has been around for getting close to 40 years. Well, now we have multiple facilities across North America, and within our greater ultralight battery umbrella, we're worldwide. So we have specialties in many disciplines, including drilling, batteries, hazardous locations, ruggedized equipment, medical, and just other mission critical applications. So do keep reaching out, keep connected, and whatever demanding application, together we'll get that job done too. So today we're going to discuss lithium battery safety and handling. Primarily we will be looking from the angle of downhole drilling applications, but the information we're going to discuss it's applicable to most any of your lithium battery applications. Your organizations will each have its protocols around safety. As we discuss these Class 9 dangerous goods today, please ensure that you take it upon yourself to be familiar with those terms and things that your own organizations have laid out in this regard. So today we're going to cover just in a general sense how a battery works, the safety implications of lithium batteries, battery leaks and explosions, hazards that you may have to deal with, and the storage, shipping, and disposal. So kind of that full cycle of your use of these things. Downhole batteries. So downhole, for those not necessarily in the drilling industry, is what it sounds like. Batteries down in the hole in the drilling environment. We manufacture these primarily in our Calgary and Houston offices, where we're close to on-site for a lot of the places that you guys are going to be working through. But we're capable of manufacturing these at any of our facilities. We supply batteries for the drilling market, measurement well drilling, logging well drilling, and memory gauge market as well. How safe are lithium batteries? Well, that's a pretty loaded question there. But when handled correctly, these things are really safe. So I find myself always kind of having to be on that line of scaring some folks to make sure that they're ship shape and they're handling it right, and easing the concerns of others who maybe have gotten a little over concerned about these things. So a happy medium approach is where we want to be. We want to realize that there are potential hazards, but the likelihood of a hazard is extremely low. So these things are built to handle extreme environments, and there's generally little on the surface aside from what we'll talk about today that you're likely to encounter. Certainly, physical abuse, mechanical abuse, thermal abuse can all result in the kind of troubles that will give us a bad day. So we definitely want you all to be aware of the risks and just give them that healthy respect that's required as we go through our day. In a very general sense, a battery generally is a cathode, an anode, and an electrolyte. We have a separator that's usually a poly or a paper type material that will keep those two things from coming together. The lithium thionyl chloride battery, which is probably 90% of what folks are going to be talking about when they're in that primary battery world. There's also the sulfuryl chloride batteries that have similar nature to this. So this can cover along that ground as well. In this battery, it's a little different that we actually have a liquid cathode here. With the thionyl chloride is doubling as that electrolyte solvent and the oxidizing agent. The carbon cathode is functioning as a reaction site catalyst so that we can deposit our solid reaction products and put them away nicely. There's generally 2 electrolyte salts that are going to be used, and that's going to be our lithium chloride and our gallium chloride. The gallium tends to be a little bit more expensive on a per cell basis, but tends to have less issues around passivation and things like that. So cell design. So there's generally, we're going to go through the 3 main categories of cell design just to kind of give us the basis for how these things are put together. We talk about rate capability, which is really how much current we can pull out of these things. And for the most part, it's that surface area where anode points at the cathode. The greater that is, the greater the current we're going to be able to draw from these things. But like anything, if you have more common surface area, you're going to have more separator, more other things that take up real estate. And so you'll generally have, as rate capability goes up, your capacity is going to have to go down as we fill these cells with things that aren't necessarily part of the actual reaction. So a Bobbin cell generally has the least surface area, and we consider this to be the low rate design. It's generally our least expensive cell that we're going to work with. It generally has less surface area and less parts that can go wrong, so they're often considered to be the most rugged. But because of that surface area being quite low, they're going to have the lowest ability to generate current flows. Dual anode is very common in our drilling environments, often known as the moderate rate design. And it's more or less just creates kind of a C as we have the anode wrap around that cathode and kind of doubles up the surface area that the anode is pointing at the cathode. So we can achieve greater currents out of this. Cost is a little bit more tricky to put these together, so the cost goes up a little bit. Also very rugged, and the capability for current is somewhere in the middle of the 3 designs. The spiral cell, we affectionately call this the jelly roll, will have the highest common surface area where the 2 are pointing at each other. And as it looks here on your screen, it's essentially the anode and cathode with a separator, and it's rolled up in order to get the absolute greatest cathode pointing at anode that we can get. As you can imagine now, there's a lot more separator in here. So the overall reactive material is far lower. So we're going to have less actual capacity in this cell, but the highest ability to generate current. These are generally their kind of the highest cost cells. Also very rugged. I know they all said very rugged, but they're all very rugged designs, right? These cells are all tested to an extremely high shock and vibe level that goes far beyond just mere transport. So as we look at a cell, there's a lot of things going on here as what the components are. Some of the main things we're really going to consider today that you'll want to understand is that if you look at this cell, pretty much everything on that outside is generally negative. The only part that's actually positive is generally that pin that comes out of the top. So separating those 2 things, just like on high voltage lines where you see ceramic discs holding the lines away from it, where there is a small glass donut generally that will go around and separate what we call that can from that positive tab. So this is a very important component of the cell. It obviously isolates your positive and your negative so that we can't get into short circuit scenarios. But it does represent a potential weakness in the cell. The glass in these things is pretty fancy. It's doped so that the thermal expansion of the glass is generally very much in line with the thermal expansion of the can. So these things can essentially grow together But it is a place where little fissures can potentially get established if things are going wrong. So that can generally be a place where we can see some leakage. Other places of potential concern can be where the top slugs that are on the metal lids are usually laser welded to what we call the metal can. And so if the heat or the settings are slightly off, that can, of course, potentially have a weak point of the cell.